Well, to continue with our discussions on non-ideal solutions, or more specifically on the Van Laar and the 3 suffix modulus equation, we were trying to find out how to find out activity coefficients using this. Now, before I start, I would like to mention once more that both the Van Laar and the 3 suffix modulus equation, they are firstly simple, they contain only 2 adjustable parameters and they are used extensively to correlate gammas. Now, among these two, it is important for you to remember that Margulis equation it is usually used for symmetrical systems. When A12 is almost equal to A21, and Van Laar equation it is used usually for unsymmetrical systems. These are just as guides as when you should apply which one, and it is also important for you to remember that Van Laar equation, although it is used for unsymmetrical systems, it is not applicable for ln gamma exhibiting maxima or minima. Under this condition, Van Laar equation is not applicable, right? And we find that since both of these equations, this Van Laar and 3 suffix Margulis, they contain only 2 adjustable parameters. So, therefore, we find that the constants which are nothing but A12 and A21 in one case, or the B12 and B21 in the other case, they can be determined from a single measurement of VLE composition plus P1 saturated, P2 saturated data. So, we will be doing a few problems shortly to just to show you how from a single measurement of VLE composition along with either the Antoine's constant or data on saturated vapor pressure of component 1 and 2, just for a single measurement we can find out these constants, we can find out these constants, as a result of which we can generate the gamma values using either the Van Laar or the 3 suffix Margulis equation, right. Now, coming back to our original discussion, what did we find out in that particular case? We had written down the Van Laar and the 3 suffix Margulis equation in a term which will be friendly, or rather in a form where we can find out the constants very easily. So, we found out that if we write down the 3 suffix Margulis equation in this particular form, then we find that more or less ln gamma 1 by x2 square should be linear with x1, and from the intercepts at the two extreme positions of x1 equals to 0 and x1 equals to 1, we should be in a position to find out two constants, right. Same thing applies for gamma 2, ln gamma 2 by x1 also. Now, I had given you a problem, if you remember, that it is always possible that A12, A21 determined from this particular graph may not be same as the A12, A21 determined from this particular graph. So, therefore, under that condition, what do? We try to combine ln gamma 1 and ln gamma 2 and try to generate a single equation from where we can find out A12 and A21. What is the way of combining ln gamma 1, ln gamma 2? If you recall the original expression of G by RT, what was it? G by RT was equal to, if you remember, it is nothing but x1 ln gamma 1 plus x2 ln gamma 2, isn't it? So, what can we do for this particular case? We can write it down as, if you substitute the expressions of ln gamma 1, ln gamma 2, then in that case we find that this will be equal to x1 x2 A21 x1 plus A12 x2, right. And from there we find that if we have combined these, then in that case we can plot your suppose we plot GE by RT, suppose this is x1 x2 by G by RT, right? No, sorry, not this. If we plot GE by RT x1 x2, then what do we have? Suppose we are plotting it in terms of x1 G by RT x1 x2, this whole thing taken on this particular side. So, in that case what do we have? We have a single equation from which we can find out A12 and A21 just from the two extremes. So, therefore, this gives us A12, this gives us A21, an averaged A12 and A21 considering the variation of both gamma 1 and gamma 2 with composition, right. So, what do we do from here? We can, if we have one data on x1, y1, etc., etc., and then from one set of data we can find out these two. We will be doing a problem shortly, and once, or rather I can show you the problem in this particular case. It is a ethanol, it's a ethanol benzene problem at 40 degrees centigrade. You are required to generate theoretical VLE data. Say for example, you are required to use the 3 suffix Margulis equation. You know P1 0, or rather you know P1 saturated, you know P2 saturated. You have data on x1, you have data on P, right, and you are supposed to find out the y1 values using Margulis equation as well as Van Laar equation, which will be which we will discussing shortly, and then you need to compare with the experimental data. Fine. So, therefore, you already know P1 saturated, P2 saturated. Now, from here what do you know? You can find out gamma 1 equals to, it is y1 P by x1 P1 saturated. So, therefore, you can find out the individual gammas in this particular case. For example, say for instance, the gammas in this particular case, it will be something of this sort. You can check it up and you can find out. The corresponding gamma 2s also can be found out, and once you have, so how do you find out gamma 2 and gamma 1? You are first supposed to find out G by RT by x1 x2. So, what do you do? Once you know these things, you can find out gamma 1, gamma 2, and then from there you can find out G by RT as, sorry, x1 ln gamma 1 plus x2 ln gamma 2. Then you know the G by RT for the different x1 y1 values. For example, in this case it is about say 237.3, 219.4, 196.3 and so on and so forth. You can just calculate. Once you have calculated this, then what do? You simply plot G by RT x1 x2 as a function of the different x1s that you have. You find out the straight line, and from this particular straight line you find out A21 and A12. Once A21 and A12 have been found out, then for other particular, then from there you can generate the gamma values for the different compositions, and once you have done that, then you can find out y1 for each case, and you can compare with the experimental y1 values, right. So, therefore, this is the way that you are supposed to work out in this particular case. We know that for just check up, you will be finding A12 in this particular case as 2.181, A21 will be 1.37. So, once you know them, you find yi's or y1s, whatever it is, and then you can proceed and you can find it out. Fine. So, this was about the Margulis equation. Now, what about the Van Laar equation? Just look at the Van Laar equation the way that I have written down. In this case, what do you expect? How do you expect to proceed in the for the case of Van Laar equation? So, in this particular case, just look at the equation. Can we write it down in this form? Say suppose if we can write it down as ln gamma 1, which is equal to, I will just write down the equation once more. It was B12 by 1 plus B12 x1 by B21 x2 whole square, and this was ln gamma 2, it was b21 by 1 plus b21 x2 by b12 x1 whole square. Just these three equations, it will be good if you can remember them. Agreed. So, therefore, can you just write it down in this particular form? Just check up if you can do it in this particular form, root b12 by b21 x1 by x2, and same way 1 by root ln gamma 2, this will be 1 by root b21 plus root b21 by b12 x2 by x1, right. So, in this particular case, what can we do? We can plot 1 by root ln gamma 1 as a function of x1 by x2, and then from there we can find out from the slope and the intercept. Similar way, we can plot out 1 by root ln gamma 2 as a function of x2 by x1, and then from both of these we know that the slope in this particular case it's going to be, or in other words, we know that at x1 equals to 0, the intercept here will be root b12, and at x1, and so therefore from here we can find it out, and again from here we can find out b21. Again there is the problem that from the slope and intercept, the values that we have got, they might be different when we are using this equation or this graph and this graph. So, what we need a proper averaging or a proper summation using the G by RT value, right. So, for this case, again suppose we use GE by RT equals to x1 ln gamma 1 plus x2 ln gamma 2. Then what do you find in this particular case? You find that suppose we plot RT x1 x2 by GE, then in that case this will be equal to 1 by b21 x1 plus 1 by b12, sorry, b12, this x1 is here, this is x2, right. So, therefore, in this particular case, if we plot RT x1 x2 by GE as a function of x1, then we find that we get a straight line whose intercept here will be b12 and the intercept here will be b21. So, therefore, in a very similar manner, if we take up this particular data, here in this particular case also, you can very well from here you can find out gamma 1, gamma 2, you can, the G by RT is the same. Then instead of this particular thing, in here you need to plot x1 x2 by G by RT as a function of x1, and then from the intercepts you are in a position to find out b12 and b21. Once you have found them out, then from there you can find out the gammas, from the gammas you can find out y1, and you can compare with the results in this particular case. So, you can try out this problem and you can find out what are the more or less what sort of how comparable you find the experimental data with the calculated data that you find, and then you can compare. The thing which you need to do is you need to find out y calculated, okay, and then once you find out y calculated for each case, then in that way the variation can be found out from delta y bar equals to y I experiment minus y I calculated, the sigma of the whole thing divided by n. So, you are required to find out this thing, this delta y bar for 3 suffix Margulis and for Van Laar, compare the two, and then you can comment on the suitability of the two equations. In the similar way, there is also one more problem, you can take it up. The previous problem, it had given you data, it was an isothermal data. Here we have got a acetone CCl4 mixed system, and we are providing you isobaric VLE data, and in this case the P1 and P2 saturated are not provided, the Antoine's constants are provided, from which you can find out the P1, the P saturated for acetone and the P saturated for CCl4, and then if you are using van der equation and 3 suffix equation, in the same way you can find out you can find out the constants A1 to A21, constants B1 to B21. Once you know those particular constants, we assume that for they do not vary with temperature. As a result of it, at x1 at these two values, you can find out, when you know the x1, from there you can find out gamma 1. You have found out gamma 1, gamma 2 using this particular data, and then from these gamma 1, gamma 2 you can find out A1 to A21. In the other case, you can find out B1 to B21. Once this particular thing is available, then you can find out gamma 1 for any particular condition, gamma 2 for any particular condition, and from there you can find out y1 equals to, and then you and then once you know y1, you know everything, you can find out temperature, and you are supposed to compare with experimental data and find out how accurate it is. So, this is the general way by which we find out the activity coefficients. We can use the 2 suffix modulus equation when the situation, when it is not very far removed from ideality. When it is slightly more removed, we slightly modify the 2 suffix modulus equation and try to use the 3 suffix modulus or the van der equations. For the purpose of the class, it is sufficient for you to be involved with these 3 types of equations. For the other equations, it is just important to know when we use the other equations. For example, Wilson's plot or rather Wilson's equation, it is used when there is a temperature dependence of the constants are quite significant. The NRTL is used when the two particular components, they are not randomly mixed, and so on and so forth. But for this particular class, we will be concerned with 2 suffix modulus equation, 3 suffix modulus equation, and the van der equation. Now, apart from this, I would also like to mention one more interesting thing. When there is a remarkable or significant deviation of the solution from ideal behavior, what do you expect under that condition? Let us see what happens. For that particular condition, we find that whether it is a negative deviation or a positive deviation, we find that see, the curve has to start from it has to start from P1 P2 saturated, it has to end to P1 saturated. Now, when there is significant deviation from ideality, then in that case we find that very frequently the curve, it either passes through a maxima when there is positive deviation from Raoult's law, or it can pass through a minima when there is a negative deviation from Raoult's law. Under this condition, what happens? When there is such a significant deviation from Raoult's law, we find that there is either a maxima or a minima, and if we plot the corresponding temperature curves, we find that in those particular Tx plots also, we find that the temperature or at the boiling point of the mixture will be either much greater than the boiling point of the individual components, or it will be less as compared to the boiling point of the individual components. So, accordingly we find that at this particular point where we encounter a maxima in the Px curve, for example here, or we encounter a minima in the Py curve, what do we find? That for this particular situation, can we not write down dP dx1 equals to 0? What is this P? It is just the summation of the partial pressures. So, therefore, we can write it down in this particular way, from where we can write down dP1 dx1 is nothing but equal to dP2 dx2. Agreed. From Gibbs to Hem equation, what do we know? Just remember one thing, repeatedly during our entire discussion on ideal as well as non-ideal, particularly for non-ideal solution, for everything we are coming back to Gibbs to Hem equation. So, that shows the significance of this equation as far as phase equilibrium thermodynamics is concerned. From Gibbs theorem equation, what do we know in terms of fugacity? One more thing I would like to mention, we are using Gibbs theorem equation either in terms of chemical potential or in terms of fugacity or in terms of activity coefficient, just to find out some data when other data are known, or to test the thermodynamic consistency of VLE data, which we will be discussing in the next class, or maybe to prove certain things which are not very self evident, as we will be doing in this particular case. From Gibbs theorem equation in terms of fugacity, we know that the equation is this. This equation for low to moderate pressure, what happens? Fugacity becomes partial pressure, Pi equals to 0. For binary mixtures or binary solutions, whatever you say, this reduces to x1 d ln P1 plus x2 d ln P2 equals to 0, right. So, from here what do we get? We get x1 d ln P1 dx1 plus x2 d ln P2 dx1 equals to 0, or in other words, can we write it down as x1 by P1 this equals to minus x2 by P2 dP2 dx1, agreed? Or in other words, can we write it down as dP1 dx1 by dP2 dx2 equals to x2 by P2 by x1 by P1, this is equal to 1. Now, what is this P1 by P2 equals to? This P1 by P2, it is nothing but equals to y1 by y2, isn't it? Because it is important to remember that we can substitute these P2s with y2p. So, therefore, what do we get? We get x2 by y2p by x1 by y1p, this is equal to 1. From here we get x2 by y2 equals to x1 by y1, or x2 into 1 minus y2 will be x1 into 1 minus y1, and from this equation what do we get? We get that at the point of azeotropy, where this particular equation is applicable, x equals to y. In other words, x1 equals to y1 or x2 equals to y2. So, therefore, what do we find? We find that at the point of azeotropy, definitely there is a maximum or a minimum in the pressure versus x1 plot. When there is a maximum, quite naturally the boiling point of the solution under this particular condition, it will naturally be less as compared to the boiling point of the pure components. So, therefore, for positive deviation of Raoult's law, what do we get? We get a minimum boiling mixture. In the same way, for negative deviation of Raoult's law, we will find that the temperature of the solution, the boiling point of the solution at the point of minimum pressure will be higher as compared to the boiling point of the pure components. So, therefore, we are going to get a maximum boiling azeotrope under this particular condition, fine, and accordingly we find that for these under these two conditions, under the conditions of your minimum boiling azeotrope, for positive deviation we have a minimum boiling azeotrope, and at this particular at this particular condition we find that there is a maximum in the pressure curve, that at this particular condition the boiling point is much less as compared to the boiling point of the pure components, and for this particular condition we find that the equilibrium curve, it coincides with the diagonal line, as a result of which x equals to y under this condition. In the similar way, we find that when there is a negative deviation from Raoult's law, under that condition what do we find? For a negative deviation from Raoult's law, we have a maximum boiling mixture or a maximum boiling azeotrope, and here also its x1 equals to y1 under this condition. Now, this gives you a very fortunate situation. What do we know? We know that x1 equals to y1 at point of azeotropy, right. What is gamma 1 equals to, can you tell me? It is y1 p by x1 p1 saturated. when x1 and y1 are same, then in that case gamma 1 it's simply equal to P by P saturated. So, therefore, you see that when there is a large deviation from Raoult's law and we actually encounter azeotropes, be it a maximum or a minimum azeotrope, we find that gamma 1 and at the point of azeotropy can be obtained as a ratio of the total pressure and the saturated pressure of that component. This is gamma 1, this is gamma 2. So, once at the point, once we can locate the point of azeotropy, we can find out gamma 1 and gamma 2 at that particular points. Then for these 2 points, once at the point of azeotropy gamma 1 and gamma 2 can be found out, and we have selected a proper excess Gibbs free energy model. It can be either Van Laar or Margulis. So, therefore, if we know gamma, we know x gamma 1, gamma 2, we know x 1, we know y 1 at the point of azeotropy, then we should be in a position to find out either A12, A21 or B12, B21 depending upon the model that we have selected. And once we can find this out, then from these we can find out gamma 1, gamma 2 at other conditions, from which we can find out y1, y2, if P is not given then P, if T is not given then T under that particular condition, right. So, therefore, the calculations become pretty simple under these conditions, and I have just jotted down, we will be doing few more problems on 2 suffix Margulis equation and the under conditions of azeotropy. These problems are pretty simple and we will be doing a few of them in your assignments, and if you have further doubts regarding these problems, you are always welcome to ask us during either you can upload the questions and we will be glad to answer those questions. Now, here I would like to show you that rather I have just jotted down the methodology which is used in order to solve the vapor liquid equilibrium problems under isothermal conditions, under isobaric conditions and also at high pressure. Now, at high pressure what happens? We cannot replace fugacity with pressure under this condition. So, therefore, for these particular conditions, more or less usually when we are dealing with hydrocarbons, what we do is we try to express Ki in terms of Yi and Xi, and we find that this particular Ki, this accounts for the non-ideality in the liquid phase, it accounts for the non-ideality in the vapor phase, and very frequently several Ki plots have been suggested for hydrocarbons. We are in a position to rather you will be in a position to find out the plots, and so therefore, yeah, just I will be undoing it and I will be doing it once more. Yeah, so several K plots are available for different pressure and temperature conditions at low temperature range and high temperature range, from which K can be found out and the VLE at high pressure can be worked out accordingly. And the bubble point and dew point calculations we have been discussing for binary mixtures. If you are going for multi-component VLE data, the same procedure is going to apply, just we need to remember that instead of working with 2 components, we will be working with more than 2 components, and for this particular part the determining the for these particular cases we find that determining this sigma xi equals to 1 and these particular checks are particularly very important for these particular cases, right. And very frequently what we do in this particular case is that I have written down the algorithm for bubble point estimation, and also we have written down the algorithm when we are using the Peng-Robinson equation of state. I have also written down the steps for finding out the dew point estimation, the algorithm for finding out the dew point dew pressure calculations, and also for the flash calculations. right. So, therefore, you can use these particular algorithms, and you can find out the VLE data at high pressure and the VLE data for multi-component systems, remembering very well that the VLE data at low pressure that has been discussed for binary systems is applicable in this particular case. When we go for multi-component systems, then in that case we have more number of equations, more number of equilibrium relationships, and as a result of which, with this more number of equations, we can find out the different gammas. When we are dealing with high pressure, then instead of pressure we have to use fugacity. But for this particular class, usually we will be concentrating on binary solutions at low to moderate pressure. Fine. And when we know that there is a point of azeotropy, the calculations become simpler. For the purpose of this class, it will be important for you to remember that we will be primarily considering, once more I repeat, 2 suffix Margulis equation, 3 suffix Margulis equation, and the Van Laar equation of state. Thank you very much.